This is Lab 3, Black Hole Orbit. The main question that this lab asks is, given the data of a star's motion around a black hole, what is the mass of the black hole? This lab is centered on using computations in the computational model to estimate the mass of the black hole. Using the given values, we can construct a computational model of the star's orbit. We find the force of the black hole acting on the star using physics principles, which will be discussed later. We assume that this force is the only force acting on the star, so it acts as the net force on the system. Using Newton's law of universal gravitation, we can solve for the black hole's mass by algebraically manipulating the equation. After all the calculations, the black hole's mass was found to be about 3.7813 times 10 to the 31 kilograms. This lab once again utilizes the fundamental principle of physics, which is Newton's second law. More specifically, the momentum principle is used. You can see the sequence in rearranging the original equation to find the equation for net force, or the change in momentum. Ultimately, we can see that net force is equal to the change in momentum divided by the change in time, or commonly stated as dp over dt. Newton's law of universal gravitation is also used. This equation, when rearranged algebraically, will give us the mass of the black hole. All of the other values in the equation are either given to us or calculated. The values given to us start with the star's position data file. This file gives us the x and y position of the star as it orbits the black hole. The time between each set of points is 1 day, or 86,400 seconds, as shown in the third point. The star's mass is given at 1.989 times 10 to the 30 kilograms, and the black hole's position is also given. Using the given values and the physics principles mentioned earlier, various calculations are done to ultimately solve for the mass of the black hole. The star's velocity is calculated by finding the change in position of the star between two data points and dividing it by delta t. This is done for both the x position of the star and the y position. With this, we can initialize the initial and final velocities of the star. The star's momentum is found by simply multiplying the velocity by its mass. Again, we can initialize the initial and the final momentum of the star. dp dt is found by dividing the change in momentum through the final initial momentum found in the second equation and dividing it by delta t. F net is set equal to dp over dt, as shown in the physics principles slide earlier. F net and dp dt can be broken down into its parallel and perpendicular components, shown here. The parallel and perpendicular components will be used to construct the arrows displaying the parallel and perpendicular components while the star orbits the black hole. All of these calculations are translated and used in the Python code to construct the computational model. This part of the code displays the first while loop of the code. It calculates the velocities of the star during its orbit. The velocities, both x and y, are placed within their respective lists. They will be used later. Much of the calculations shown earlier are used in this section of the code. The second while loop of the code calculates the momentum, net force, and the parallel and perpendicular components. You can see where in the code the calculations or equations are translated by the arrows shown. The final part of the code will calculate the answer to the lab question. Using given values and the force calculated, the mass of the black hole can be calculated and printed. Newton's law of universal gravitation is rearranged to solve for the mass. The mass of the black hole was found to be about 3.7813 times 10 to the 31 kilograms. Here is a short sequence of the computational model displaying the orbit of the star around the black hole. As you can see, as the star gets closer to the black hole during its orbit, the force becomes larger, as shown in the increase of the size of the arrows. If the black hole in this lab was removed and replaced by a different black hole in the same location, and the star's motion and mass remained the same, there would be no difference in the new black hole's mass and the old black hole's mass. If all the original positions, velocities, and momentums and net force stayed the same values would be used in the equation, giving the same mass. Fnet perpendicular, Fnet parallel, and Fnet are different from dp over dt and its components because forces are what cause the change in momentum. dp over dt is calculated from the observed positions, but Fnet is a force that causes the specific observed motion and its change in momentum. dp over dt and that force, however, do have the same magnitude.